Hey scientists, how you going? I'm good, thanks very much for asking. Guys, today we're going to look at secondary forces, continuing on from last video lesson, which was looking at dispersion, and we're going to chat about dipole-dipole and hydrogen bonding. So this is where we left off last time. We had dispersion forces as forces that exist between non-polar covalent molecules. The explanation is due to temporary dipoles being formed by electron movement. And we have an example of methane, which is CH4, and the strength of those is weak. If you haven't already done so, I'd like you to pause the video now and get this content from the last lesson into your notes. Sorry about that. So the dipole-dipole interaction is the first thing we'll look at. Now, dipole-dipole interactions occur between polar molecules, which we've discussed in a previous lesson. In polar molecules, the oppositely charged ends of the dipoles are attracted towards each other. So your permanent dipoles that are created within the molecule, you've got a force of attraction there. The electrostatic forces of attraction between the oppositely charged ends holds these molecules together. An example of that is HCl, which is solid hydrogen chloride, or in a liquid form could be hydrochloric acid. So here's our simple representation of our molecule. Now this is a polar molecule, and you've got a permanent dipole with your delta plus and your delta minus, and we have covered polar molecules previously. So that dipole is going to cause a permanent partial charge on the hydrogen and the chlorine due to uneven sharing of electrons. Remember, polar bears are greedy. So what we're going to have here is an attraction between two neighbouring HCl molecules. So the slightly negatively charged end of this HCl is going to be attracted to the slightly positively charged end of this HCl molecule. And you represent that force of attraction, that intermolecular attraction. Remember, inter forces between molecules, by a dotted line. So this is a dipole-dipole interaction here. So to summarize your dipole-dipole, they occur between polar covalent molecules, and it's got to do with electrostatic force. An example is HCl, and the strength stronger than dispersion. They're still relatively weak, but they're stronger than dispersion. I'd like you to pause the video now and record as my cat comes in for a cameo. So the next part of intermolecular force we'll go into is hydrogen bonding. Now hydrogen bonding is the strongest kind of intermolecular force. There's actually one slightly stronger kind, but we'll go into that a bit later. It's a particular type of dipole-dipole interaction. It's a special type of dipole-dipole interaction. Now this occurs between molecules in which hydrogen, now you have to have hydrogen because it's hydrogen bonding, that makes sense, is bonded to a nitrogen, an oxygen, or a fluorine molecule. You might say, how am I supposed to remember that? Nitrogen, oxygen, and fluorine out of all of the elements on the periodic table. And the acronym to remember that is NOF. Now, I don't mean the National Osteoporosis Foundation. I'm sure some of you are thinking that. I'm not talking about NOF Energy. I know a lot of you guys have been considering getting with NOF, but it's not NOF Energy. And I'm not talking about the original NOF leather bags. No, no, no. I'm sure they're an exquisitely expensive and luxurious product, but that's not what I'm talking about there. I'm talking about nitrogen, oxygen, and fluorine. Hydrogen bonding. I'm really sorry for that. Hydrogen bonding, it occurs between these molecules, is because they're all highly electronegative. Nitrogen, oxygen, and fluorine are highly electronegative. The three most electronegative, so the greediest elements in terms of electrons, that's why we're talking about those. Therefore, the covalent bonds between hydrogen and atoms of these elements are highly polarized. So hydrogen atoms in these molecules will gain a large partial positive charge. So the delta plus is stronger than it is for a normal dipole-dipole interaction. Also, and this point is important and is often understated, nitrogen, oxygen, and fluorine have at least one lone pair of electrons. You need to have a lone pair of electrons for this hydrogen bonding to work. So nitrogen has one lone pair, oxygen has two, and fluorine has three. So here's a diagram of how it works. We've got two water molecules, and you've got a dotted line connecting them, which is the hydrogen bonding force. Okay. Now, usually for secondary interactions, we don't call them bonds because they're not as strong as bonds. So dispersion force, dipole-dipole interaction. Hydrogen bonding, though, is a secondary force, but because it's quite strong, we actually use the term bond. So it's close to the strength of a primary bond. Not quite, but it's getting there. So you've got hydrogen, which you need for hydrogen bonding. Okay, so we've ticked that. You've got an oxygen attached to a hydrogen. So that fills in the NOF rule. O for oxygen. Oxygen has a lone pair. So the lone pair, one of the lone pairs of the oxygen attracts to the hydrogen on a neighboring molecule, which is connected to an O. Okay, so this H is connected to this O, so highly electronegative. Therefore, this delta plus is large. Okay, and therefore you've got a strong interaction between a neighboring O and the lone pair is here. Now the reason why the lone pair is important is because it's just space. It's non-bonding electrons, it's extra space for that interaction, that bond to actually go to. Okay, so that's an example of a hydrogen bond. Here's one more. We've got a water molecule once again, and we've got NH3, which is ammonia. Okay. Now these wedges and the dotted lines here just indicate the 3D spatial arrangement of that NH3 molecule. So we've got an N, and that's connected to a H, and the N is highly electronegative. So the NOF rule is adhered to, and also over here we've got an O connected to a H, so the NOF rule is adhered to. Okay, this is extremely positive, and you've got that hydrogen bonding connection there. Okay, so that's an example of another hydrogen bond. So that's the finale here. I've got a summary for you, and I'd just like you to quickly pause the video and jot this down in your notes. So I'll leave you with this thought. We've talked about different types of intermolecular and intramolecular forces. The question that we had initially, why don't oil and water mix? Now, to help you answer this question, I'll tell you a little bit more about them. Water, we know that water is a polar molecule, and we just talked about the hydrogen bonding forces that exhibit between water molecules. And we've got oil. Now, oil is a non-polar molecule. Okay, so try to use your understanding of intermolecular forces that exist between oil and between water molecules to try to explain why they don't mix with each other, why they would rather connect and attract each other. Good luck, and I'll look forward to checking out your responses in class. See you later.